Right, so let me explain how this T-gate computation using magic states works. So let's first go over the main idea over using a simple example. Imagine the following circuit. So we have a state psi. Our goal is to apply the X gate to psi, but we don't know how to apply the X gate. Instead, we want to do it using simpler building blocks, arguably simpler, which are either the C0 gate or a measurement in the computational basis. So let's see how we would do this. So first here, what I drew for you is a circuit which just swaps the two gates. So you control the two states. You control on the plus state here, and controlled on plus, you apply a NOT on the psi state. Then controlled on the first wire, you apply a NOT on the second wire. And if you evaluate what happens, then whatever the psi state is, and this is a plus, at the end of the circuit, we've switched the plus and the psi. All right, fine. Now let's imagine that instead of applying this last C0 here, let's not do it. Instead, let's measure the first wire in the computational basis. So I perform a measurement here, and this measurement returns an outcome C, which is a bit in 0, 1. Then what do I know? Well, I know that if I had applied a C0 gate, instead of doing this measurement, the state here would have been a psi. Now I measure and I see a C. It means that the state is psi, except if C is 1, in which case it's X psi, because the C0 would have given me psi, and C0, if the first wire is 1, corresponds to applying an X on the second basis. So if C is 1, I have X psi. If C is 0, I have psi, which means I have X C psi. So in this way, I've implemented a X to the C gate on psi, where C is just a random bit, the outcome of that measurement. And what did I need in order to do that? Simply the C0, the measurement, and preparing what is the magic state for the case of this gate, the plus state. So that's what we'd call the magic state here. Okay, so how do we do this for the T gate now? Recall that the T gate was equal to this gate. Well, there's a similar circuit. We want to apply a T gate to a psi state here. Here's how we'll do it. We'll prepare another magic state. Now the magic state is the plus state to which we applied the T gate. So note that I'm using a T gate to implement a T gate. The important point here is that this T gate is applied to a pure single qubit plus state. That's something we can ask our verifier to do. It's just a single qubit operation. This psi here can in fact be a reduced density. It's part of a global computation, so it's something we don't have access to. The prover is storing all this to us. So this computation we can perform, and then we ship over to the prover. The prover has psi, is supposed to perform a C0 on the state we sent it and the psi, followed by a measurement. This measurement is going to return an outcome C. This outcome C, the prover returns to us, and then depending on C, the prover is also, so that goes to the verifier, and then depending on C, the prover also applies a controlled P gate on the wire that used to contain the magic state. So that's the whole let's apply a T gate operation, and if you calculate what this does to the state psi, what the outcome of this here, wire is exactly what we wanted. So it's the gate T applied to the state psi plus some corrections. So there's some Pauli correction, XC and ZC. And this is why we need the prover to report the outcome C to us, because this is okay. We'll just have to update our one-time pad key by adding C to the bits for the X basis and C to the bits for the Z basis. But in this way, we've managed to apply a T gate to whatever was on this wire here, simply by preparing this simple 1 qubit magic state, sending it to the prover, and then instructing the prover to perform these operations. So that's the circuit for sort of doing the T gate in the clear. In practice, you want this to be blind, so you don't want to be sending always the same state to the prover. This is because of the test runs in the computation and Hadamard basis. So what we'll use is a little bit slightly more complicated basis, which will also involve encrypting this magic state and taking the effects of this encryption into account, propagating it through the circuit to update the keys in a slightly different way. So in practice, we use something slightly more complicated, but that's basically the idea. How you can delegate the implementation of a complicated gate to a prover by simply preparing so-called magic states that let you delegate this computation.